And putting it up on YouTube. I saw you put the link. That's good. And putting it up on YouTube. Right. Okay, so
Hi, Prof. Min. Hi.
yeah. Afternoon, everyone. Okay, so it's 1 o'clock by the time on my computer. So I think we can go ahead and start. So today is our first day for CS6101 for the second half of the semester. And we have the first set of speakers set up for the conversational recommendation system lecture. So I saw on the preparation channel from Slack that there's some ordering issues. I hope you guys got it sorted out. Who is going to present? So and just check with the folks. Is Victor and Chengxin and Nham presenting first, then followed by Hongfu and Chauri and Joel, and then
yes, Prof. Yes, Prof.
Okay, and then we have our final paper from Zijin and Gangyi. Okay, great. So it's all yours. You can take it away.
Yeah, okay. So let me share my screen first.
Okay, we're going to make it editable. I think Joel says it's not editable, so let's just double check that. Yeah, it's not. Okay, I'll change that.
Okay.
Here. Okay, Joel. So if you hop on the slide link, it should be fine by now. You may need to refresh.
Sorry, I think let me check one more time. Yeah, so are you having a look at the correct one? The presentation?
Can you the screen?
Yes, called user memory reasoning.
Yeah, I see it.
So how about now? Are you seeing that same page?
Yeah, slightly different. It's a little bit cut off on the right.
Oh, but so that's my presenter small, so I need to share only the presentation one. I don't know how to do that. Well, now it's still the presenter mode.
Okay, I'm waiting for it to come in. Do you guys see Victor's screen yet? The bandwidth.
I cannot see it at the moment.
Okay, yeah. I see that.
Yeah.
All of us are looking at a black screen that says you started screen share, but we don't see the screen.
Maybe I can share screen instead.
Okay, yeah. Please. Thank you.
Oh,
sorry about that. Yeah.
Oh,
came in. Okay, well, it's gone again. So yeah, Quoc, maybe you can go ahead and share.
Yeah. Okay. Can you see the screen?
Yeah.
Yes. Okay.
See?
Yeah.
Okay.
So okay. So I will start my presentation now. Okay. So hello everyone. My name is Victor. So I'm happy to be the first one to share because I gave a general introduction for the area of conversational recommendation system. Okay. So I will go through the introduction and background for the conversational recommendation system, and after that I will pass my time to my partners who will introduce the data side methodology, followed by experiments, and finally the conclusion and discussion. Okay. Yeah, please, next one. Okay, so at the first one, I will give an introduction about the background. Okay, so conversational recommendation system, as the name indicates, it is a combination of conversational system and recommendation system. Okay, next. Okay, so and it can be divided by online part and offline parts. Okay, so for the offline part, we are only using the information provided by the user's history. So for this part, it's quite like the conventional method for recommendation system. We are using the content-based collaborative filtering or a hybrid-based method, which is a combination of both methods. And we are using those conventional methods to make recommendation based on the user's historical data. And next, yeah, this method has some weakness. For example, it suffers from the data sparsity, and it also cannot catch the dynamic change of the user's interest. And also, we have no idea what's happening on the system itself, so there's lack of explainability. Yes. Okay, so and for the online part, usually for the conversational recommendation system, the online part means the part that we use the conversation. We make conversations with the users to ask different attributes of an item, or we request feedback from the users. Or in some scenarios, when we want to make recommendation on certain items, we need to confirm with the users whether he liked the recommendation or whether he agreed with our explanation. Okay, next one. So by doing the conversation from the user side, he can also input some requests to the system. For example, he can initiate a conversation by saying that I would like search for some items like in certain categories. Or he can also make a sudden change of his idea. I used to like this kind of movie, but I don't like it anymore. So I want some new kind of movies. Or sometimes when the user is not able to make a certain decision, he can also interact with the system by giving answers to different questions and ask the system to help him decide which kind of item he would like to choose. So by doing the interactive conversations between the users, the conversation systems and recommendation systems, we could improve the dynamicity and explainability of the recommendation system. So this is the online part and offline part of the conversational recommendation system. So if most of the time we don't have a well-defined online data or offline data, we usually have a common data set that's combined, that only combines the certain historical data of a certain user. So in this scenarios, we can split the data to offline part and online part. For example, we can use the last purchase items as the online data and use all the other items that he purchased before as the offline data to train the model. And then we try to make conversation with the user to locate the last one that he would like to purchase. So that's the usual scenarios. Okay, the next slide, please. Okay, so here I introduced the general structure of a conversational recommendation system. So usually we'll start from the left part. Okay. Okay, so you can see my mouse now. So we start from the questions and answers of this is the conversational part. So after the conversation, right, usually we will use some like memory networks, or we use embedding methods to get all the information that we get from the conversation into a length factor. And based on those length factor, we either compare with all the current existing items to generate the ranking list, or we select several items to form up our own candidate set. So based on this history, we'll make a decision whether the model will keep doing a conversation with the user or keep asking questions, or we should make recommend to the users. Okay, so there are some question I want to talk about here. So first is this paper talk about memory network. So memory graph. So what is memory? Usually a memory do two things. One is to embed something to change some behaviors, to change user behaviors into a length variable. This is the first one. And the second one, what the memory do is it can update this variable from the historical data. So if he made a length variable from historical data and he makes next round of conversation, he could update this variable by the current round of memory will do. Okay. So okay. So here I talk about a few questions on the conversation recommendation system based on this paper, EAR 2020. Okay. So usually some questions important is that what attribute to ask. As a conversational recommendation system need to ask questions to the user. So one important question is he need to choose what kind of question to ask. Okay, and this kind of question can be different types. One is a binary question, like for example, whether do you like this attribute, or it can be open-ended question. What kind of phone do you like? What kind of restaurant do you like? So it's different kind of questions. And if we have no historical data of the users, means there's a cold start problem. We need to get every information from the user by asking questions. And the second problem is when to recommend items. This is also a very important question in all the conversational recommendation systems, especially for the decision part, whether you should keep on doing conversation or you should make a recommendation. Usually this problem is solved by some way like the reinforcement learning. You will learn from the behavior, you will give certain rewards for different behaviors. For example, if you will receive rewards when you recommend correct stuff, or you ask well-ranked problems, or you will receive punishment when you ask some useless questions, or when your conversation is too long, the user just quit your conversation, or when you recommend wrong stuff to the users. Okay, so and how to adopt users' feedback. This one, the users will give us different feedbacks. For example, positive feedback, negative feedback, or neutral feedback. Neutral feedback means when the user have no idea about the attribute you ask. Okay, so basically that's neutral feedback. So here I want to pose a question to all of you, right? So do you think the positive feedback is important, or the negative feedback is more important to make the decision? Anyone want to answer?
I think the positive feedback seems maybe more important. Just a random guess.
Yes, so sorry, can you repeat? I just didn't hear that.
I think the positive feedback can have more information for guiding the model to the right direction.
Oh yes, correct. So actually, according to my personal experience, yeah, it's true. Because why? Because I made another graph. That's okay. So when you are asking a positive question, right? I'm sorry. Okay, maybe I will draw this one, right? So if like this is the overall data set you have, right? We are asking a positive questions. So you are cutting the data set into some different parts, right? So this is just, so usually at the beginning of the conversation, something you like will be the small subset. means if you got a positive response, then you can locate those items in the small subset of it. If you keep asking questions and receive positive answers, you will slightly decrease the size of this one. Yeah. But if you are asking a negative question, like for example, you know like the users don't like this part, then you can only remove this small portion of this part. So I think it's very important that you try to ask the questions with positive feedback. So it's just one of the explanation. Okay. There's also like other ways to talk about this problem. Okay. So and another thing I want to talk about, because we are talking about memory graph, right? Memory graph to deal with in this conversational recommendation system has two benefits. One is that the memory graph can consider all the available knowledge about the users and item together, so that he can better serve the decision process to generate the dialogue policy. And another benefit is that memory network that trained from a certain user can be applied to different users. So you can also deal with some cold start problem. Okay, so next slide, please. Okay, so here I generally introduce some stuff that we use in conversational recommendation system. For example, the data type. Okay, so we use the historical data, means the offline part, or the dynamic data means the online part. Okay, so the offline data sometimes is implicit data, like the user's experience. User had read books before, watch movies before. It has bias, means click doesn't equals to like. So the user watch a movie doesn't means the user like the movie. Okay, explicit data is the ranking. For online one, I say binary. You can answer yes or no. Values means open-ended questions. Okay, different scenarios: a single round conversational recommendation system or multi-round. The round doesn't mean the round of conversations. It means how many times you make recommendation. Okay, so single round you can only make once, regardless of the user satisfied or not. You end the conversation. Or the multi-round you can make several recommend. Okay, so the initiator is the conversation can be initiated by the users or by the system. Okay, next slide. Okay, here is one example of a conversation recommendation system. You can see all the things that color in white is attribute to ask. So basically it's a category, and all the things colored in blue is a value or a response. Okay, so you can see that this conversation is initiated by the user by searching a phone. Okay, yes. And it's a multi-round of conversational recommendation. The reason why is because the system has already made a recommendation here, but it seems that user gives negative feedback. So he will go back to do the recommendation again. So usually when he receives negative feedback, the system won't just generate another set of items to recommend. He will keep asking more questions. Yeah, because the punishment for making wrong recommendation is much bigger than the long conversation. Okay, so the system will confirm he is confident enough to make a new recommendation. Okay, so that's the general process of a conversational recommendation system. Okay, so I will pass my time to Chengxin to talk about the methods. So any problem?
So do we want to pause there for a second? Anyone have questions about the overall framework for conversational recommendation systems? I think it's quite clear. So I think, yeah, Chengxin, you're welcome to go ahead and do the next segment.
Yeah, can I share my screen?
Okay, yeah. Quoc, do you want to try to turn off your screen? And then let's see whether Chengxin's screen share works.
So,
yeah,
is it work?
Yeah.
Did you see my screen now?
Mm-hmm.
Oh, cool. So this paper is about want to integrate the past history of the user, so can have a better recommendations for users. So first, they introduce a new data set, which is the restaurant domain contains 7.6K dialogue with 73K terms based on the real-world user behavior, and have 10 popular slots with a total of 470 values. When I say slots, the slots in this dataset can be location, category, price, and the value associated to these slots can be fast food or Thai food to the category, and the cheap or expensive to the price. So the aim of this dataset is to contain the dialog that can draw the relevance of the user history and the fine-grained user preference to update the user memory graph. So to carry the user past the behavior to harvest the large-scale dialog scenarios. So this is more details of the dataset. As we can see in the dataset, we have the dialog with history and without the history. And we can see the dialog with history may have a shorter terms, may have shorter terms with this don't have the history. So when we say a scenario consists of users, candidate elements and their associated users pass the history and values with their associated slots, user preference, and the elements, the ground truth items. So then we can construct a user memory graph with the typed entities and the relationships. So this is some details of what type of entities and relationships the graph will have. So this is an example to how to construct a user memory graph. So let's say we have a Bob user. This is the user entity, and he has the memory entity. So this is a relation that Bob has the memories, and this memory is about the element Cs. This is the element entity. So which means the Bob has visited the Cs in his past history, and this Cs had the values of the affordable and Japanese, which means it is a Japanese restaurant with affordable price, and this affordable price is associated to a slot, just we see. This one is associated to the price. So this is the user memory graph. So after we have the user memory graph, we want to update the user memory graph according to the dialog. So how to update this graph? There are three types of the segment relations: positive, negative, and neutral on the value or elements, which can connect a user to the elements. So for example, given this dialog, at the first turn, the agent asks the user, what kind of food do you like? Then the user answer, I like Thai food. So they will have a new tribal to connect the current dialogue with the Thai food, has a positive relationship. So then at the second turn, the agent asks the user, are you still interested in affordable restaurant? Then the user say yes. Then the graph will update it with this link, which connect the current dialogue to the affordable values, has a positive link. So to this end, the agent can make a reference to recommend the parcel to the user, which this element is have the values of the Thai food and the affordable price. So it can enable the knowledge reasoning dialogue policy. So in this paper, the author further introduced a baseline model to use the user memory graph for reasoning dialogue policy. So this is the framework of the proposed model, and the input of it is the past outerings up to current term and the previous user memory graph, and the output of it is the dialogue policy for the current term, namely the dialogue action and the candidate elements, values, and slots. So I did first the framework will encode the entities through an embedding layer. Just now we see many types of entities are all encoded in this type, and will also encode the unstructured utterance through a BERT, which is a commonly used the model. Then after have these embeddings, the author introduced RGCN to update the hidden state of each entity based on its neighbors, type by type. When I say type by type is about the relation type. So we have 3 types of relation. So this is the formula to aggregate the neighbors' informations. And this is the previously graph. So for the first 2 layers is about to update the graph, which means to infer the relationship probabilities to make an updated graph. So for the rest 5 layers about the updated graph is to get information for the reasoning dialogue policy. So after that, we'll have a aggregation layer, which can leverage the information in the user memory graph for predicting the dialogue actions. So this is a formula for that, which consider all the elements. So the loss of the dialogue action is the cause entropy loss, and the log loss is introduced for the relation probabilities and the items, slots, and values. So to this end, this framework can dynamic infer the graph updates, and it can suitable to the zero-shot reasoning. So that's all for my part. Thank you.
Okay, we can stop there for a second and then take any questions. I think Chengxin went over quite a lot of details of the paper, and I invite all of you, especially if you haven't read the paper, to skim it quickly. I mean, the links are on the channel, in the general channel. Do you guys have questions, especially about how the aggregation is done and how the update is done for the graph convolution network?
Yeah, can I ask Chengxin a question?
Go for it.
Yeah, okay. My question here is about, I didn't quite have an intuitive understanding about the big picture of this paper. So it is talking about the reasoning. So according to my knowledge about the reasoning, we have sort of the common sense, we have sort of the causal reasoning. So what types of the reasoning do you think, in a very concise way to describe about in this paper, what type of reasoning do you think is in this paper? To reason from the past history to the future preference or something else? Could you have an intuitive and concise description about it to help me understand? Thank you.
I think the reasoning of this paper is about they consider the history of the user, which is to make the predictions reasonable for this user. So that's what I'm understanding. As we can see from this graph, which means it can have the relations of the users past the behaviors, which is not only limited to the current dialogue. Yeah. So it's about his past history.
Using the user's past history to predict his preference in the current session.
Oh,
right?
yes.
Okay.
So let's make this clear. I think when we say user history here, we are talking about the history within the same session, right? Not across sessions. Because I think that their knowledge is limited to the information within the same session, right? They're getting user traces within a single session. Is that correct?
For this paper, it consider not only the current conversation actually. So, for example, for this link is the past the conversation actually, I think. So, which means the user has the history to visit some place, have the attribute that can contribute to this dialogue, the current conversation.
Right. Yeah, I see that in the paper now. Okay.
Yeah. Thank you, Chengxin.
Further questions about the math and what's going on? Can I ask somebody in the audience, especially our 6101 students who are support staff for this paper, you know who you are, whether you can describe or restate some of the math that's going on in the user memory graph update.
So any people want to answer this question?
Yeah, I think let's wait for a while because you know, it's great that you are presenting, but it's also good to have some interspersed dialogue, right? So we're taking this as a conversational dialogue agent type of scenario where we want to update our knowledge states with the presentation that you've already done. So I'm hoping that somebody else besides Yisong could also say a little bit about this particular slide where things are being updated.
Can I ask a question?
Please go ahead, Taha.
Okay. So for I'm actually kind of confused for the decision-taking part, right? So we have from the previous presentations, if I understand correctly, we have this rank list of decisions, but then so the system decides at each turn rather asking a question or recommending an item, right? But is it like separated within the system itself, or is it just always a dialogue act that that leads to that action? Was it clear? Did you understand my question? I'm asking if there's oh yeah, go ahead.
So you're asking whether the the decision process is always with the conversation, or
yes, or is there a separate thing that designs
so,
the
so let's take exactly this paper as an example. Okay, so for, let's say we don't care about like who initiate the conversation, okay, and we don't care about the history. So for current round, I ask a question, you answer a question, okay. So after this process, I do two stuff. One is I get the previous length variable, previous graph variables that from all the history, okay, and then I get all the information from the current conversation. Then I combine these two together. That's what the memory do, okay, memory graph do. So after this part, we fit into a neural network, okay, and we make a decision whether we are receiving positive feedback or negative feedback. So we make this decision, okay. After this decision, we have all those information. We keep using this information to make another decision. Okay, whether we are confident enough.
So there's a residual connection. If
yeah, this
okay.
separate, all the process are separate. Yeah. Okay.
Okay, I see. So then we're basically deciding whether to keep conversing or then just recommending something from them.
Yes. Depends on what we define as the confidence. So it may be different. Sometimes I think in this paper is just the ranking list, right? So you generate the ranking list. If we think,
oh, I see.
Yeah, the top items is like good enough, then we just make the recommendation.
Okay.
Yes. So maybe different, but sometimes, but usually it's when the system is confident enough, then you make the recommendation.
Okay, I see.
Yes.
And another question I had was, so what we do first is basically we just take this encoded utterance from bird, right? So let's say here in this very slide, there's this sentence saying, I like Thai food, what kinds of food do you like, right? And we take that encoding and somehow using that decide on the changes on the graph. But I cannot, so I'm not really clear on how do we go from that to the changes in the graph. So is there like another, I don't know, neural network that decides on the changes, or how is it like modeled in the behind?
So Chengxin, do you want to go back a slide or two to the one where the edges are being added and try to explain from there?
Yeah. Maybe I can see before I go back to the slides. This board is mainly about to encode the encode this sentence means encode the conversations, and the graph is another thing actually. The graph is about to link the elements and the relationships to the link all the elements and the relationship to construct construct the graph actually. So which means we have a constructed graph already, and this part is only about the sentence part.
And the sentences only add new relations, right?
Yeah.
Okay. I see. So then we are not actually adding, let's say after this conversation, user just visited a new restaurant. We are not going to add that restaurant to the graph. It's not modeled, right?
Currently I didn't say they will.
Okay.
Add, but I think maybe it's needed to add like because your person already like this recommendation, you should update the graph.
Yeah. Right. Okay. Thank you.
Thank you.
So you can see this on the slides, the earlier one where, going through the example dialogue that's in the paper, right? That's on the upper left-hand side of the slide. The agent remembers from its memory that the person was interested in affordable restaurants. So there's an edge on that part over here, right? And then suggests, based on the current dialogue from the first user turn, that they like Thai food, right? That came up in a previous turn. So that's the graph is being updated dynamically based on the conversation and based on the classification by the system about which edges to put into the graph dynamically and associate it with an edge type, right? So the edge types here are positive sentiment, negative sentiment.
Yes, thank you, Prof. Yeah, the graph will be updated. Yeah.
So how is the graph actually updated?
So I think the graph is updated according to this dialogue actually. So means just now we said this one can understand the sentence, and we can have the attitude on the relationships of the values or elements with the current dialogue.
But what I mean is how, like, so how does the system actually update the graph? Is it like, is there a prediction or something? Like, how does that part actually work?
Yeah, what is the action space? I was also actually kind of confused on that. So does it change the embedding or?
Yeah, like, is it changing like the embedding via some weights, or is there an actual like adjacency matrix or something that's
Yeah.
that's being written to?
So when they add a link, it means you need to change your adjacency matrix of the graph. Right.
Oh, I see.
So okay, so it's you are describing the graph in explicit way, like a adjacent matrix, instead of an implicit way, like a embedding of the whole graph, right?
Okay.
Yeah, because the graph is about to like you know the which relation are connected. So
Well, so
you update the graph. Yeah.
so how about, I mean, the prediction about one edge is about the probability, right? So I mean, the adjacent matrix is only the binary, or is it a probability style?
So I think here when we say they need to predict the relation probabilities is about
I
to
see.
Yeah, it's about to for the current to want to make some actions for the current terms. So
it's
this
about,
one is to predict it. So,
I see.
but I think when you update the graph, it should be the ground truth, I believe, because you already know your answers.
I see.
So then
Thank you for
how,
clarifying.
so like I'm still kind of confused how the update is done. Is there like a network that predicts like what item, like does it like output an item and some probability, and then the code uses that to update the adjacency matrix?
So I think the paper didn't mention it explicitly, but I believe from our group discussion, we believe that they so what you predict the probability of this link is for the next term what uh questions you would answer to the you would ask to the people, you would ask to the user. So after you have the answer, I think the update should be different. So just now this one is only the prediction, is not about the ground truth actually, but here you already know after the 10 you already know what the user like or what the user don't like. So from here, I think they will update the adjacency matrix.
I see. So, Chengxin, can I ask a further question? Do you think we still have enough time?
Yeah, I think it's good to get right. So yeah, please go ahead.
Yeah. Okay. So, my question is still, I mean, a sort of a limitation about their framework. So, I mean, the graph is only a sort of representation for the dialogue. Well, I think it's also very important to incorporate the information from the item side, right? So, I mean, the items, the set of items, they're also a graph, right? So, I mean, there are many guys in the Raxis domain, they're doing the pure Raxis research within a graph, a knowledge graph of all the items. But according to your presentation or the paper, I think unfortunately, the graph is not associated with the item graph, which I think here is a huge loss of the information. Do you think their framework should consider such, I mean, the item side information about the item graph? And what's your opinion about this? Yeah.
So I think the paper consider the element, some elements of the of the some values of the elements, which means their attributes of the elements. But only in single graph, is that what you mean? So you so yeah, here is the attributes actually, but I think they are limited to the, yeah, they have 470 plus values to each a social aid to, not only a social aid to the slot, but also a social aid to the item. So here is the item.
Oh, I see. So the yellow ones are items.
Yeah.
And they're a collection of attributes with particular values, right? So if you look at where the cursor is right now, CM is a moderately priced Thai food restaurant, right? So they are modeling aspects or attributes and their values, because you associate an item with these attribute value pairs. Each pair is basically one of the blue boxes that are in the graph.
I see. Okay. Yeah, I see. So they also incorporate the item side info. Yeah, great. Yeah.
Right. So in the dialogue, you heard that the agent asked, are you still interested in affordable restaurants, right? So affordable has to be connected to, I guess, moderate here, right? CM and Yaoi would be, I guess, oh, sorry, affordable is the second blue box, right? The C's and basil restaurants are affordable. Yeah, but only the basil restaurant is affordable and it's Thai food.
I see. I see. Yeah.
Yeah, the paper has actually got quite a lot of supplemental information. I agree, though, on a very cursory reading that I've just done, I don't think it's very clear exactly how the inference is done. It's clear that they annotated all of these through crowdsourcing. So they had two crowd workers play against each other to create the data set, and then other people who then annotated the data. Yeah.
See.
Okay, why don't we go to the experiments? So thanks, Chengxin, for taking down all of the questions and answers to them.
Thank you. So shall I stop my share, or you want to continue with it?
Yeah, I think I will share. I will share screen.
Okay.
Yeah, thank you.
Okay, we can see your screen, so you're good to go.
So now I will explain about the experiments, as well as the the results of the experiments. So first of all, we recall that for the user memory graph reasoner, the input will be the past dialog act up to a current turn from a user, as well as the updated memory graph after the conversation. And the dialog policy will be this Y hat A, Y hat C, Y hat S, and Y hat P. And the AC, I'm sorry?
Go ahead.
Yeah, is the space for A is for dialog acts, C is for candidate items, S is for slots, and V is for values. So I've taken out the example provided in their dataset generation to explain what is dialog acts and candidate items and slots and values. So dialog acts are the intent of each utterance. The candidate items, in this case, in the case of a restaurant recommendation, it will be the restaurant for the item. The slots will be the characteristic here, such as locations, category, price, and the values will be the value at those characteristics. So for each type of dialog act, we will give the result will be a ranking of a corresponding entity set. So when the dialog act is, for example, recommendation, we will give a ranking of the top one entity, which is an item among the item space, will be provided. So in this case, recommendation will give a restaurant recommendation. For open question, it will be a slot. And for yes, no question, it will be a value. Yeah. And so for the evaluation matrix, the first metric is called offline metric. So it's measured against a set of collected testing dialogues. So the assumption here is that we have an annotation of all the past turns. Each turn is a conversational turn. We have it as a ground truth. So the act accuracy and F1 will be measured for all the predicted dialogue acts against the annotated turn acts. And another metric is entity matching rate. So with different value of K, and K will be the top K entities measured against the testing set for each turn. But we only measure given that the correct dialog acts have been predicted, because the dialog act in turns will determine other entities. And lastly, it will be the item matching rate. This one will measure the dialog level for each dialog. It will be all the predicted items against the set of ground truth items within that dialog. And so for the next metric will be an online metric, which involves the user simulation. So here I've taken a screenshot of the example of the script for the user as opposed to the assistant within this simulation. So just to explain that for each dialog, there will only be, for the online evaluation, there will only be one ground truth item, in this case, a ground truth restaurant. And yeah, the slots and the values are similar to the definition before. Yeah, and this will be given to the assistant. But yeah, but the main thing is that this online evaluation is for dynamic evaluation, and the metrics will be the success rate to see whether that the interaction between the two simulators will be able to yield the ground truth item, which is a single item. And they use the same scenarios as offline evaluation. And the max number of turns is capped at 11 with simulations run 3 times and the results average. So this is an example dialog generated with the slots and sentiment polarities annotated. So yeah, this is just for a visualization of the dialog acts. This will be the slot as well as value. This will be the sentiment polarities, which are either positive, neutral, or negative. Yeah. And so to compare the performance of the proposed model, there are a number of baseline models. So the first one is a random agent. So this agent will just randomly pick a dialog act and also randomly pick a corresponding candidate item or slot or value as the dialog policy, the optimal dialog policy. Another agent is a rule-based agent. This agent will always choose recommendation to be the optimal dialog act, and it will select an item not tried before. So it has to memorize all the travels, and it does not use any user preference. Another method is memory network. I'm not too sure about how this is not fully explained in the paper, but references other previous work instead. So I'm just going to give a brief summary of what is mentioned in the paper. So this memory network is adapted so that we can encode our user memory graph into triples, and the memory is also updated when new triples are added. But then this network does not implement the open space policy because it has to enumerate through all the possible combination of dialog acts and entity to be used as a policy space. And the last comparison is with a pre-trained embeddings. So the author pre-trained a graph embeddings to encode the memory graph to predict dialog policy. But so this is without the RGCN layers. And lastly, it will be the proposed model. And this model is expected to be able to do zero-shot reasoning. So it does so by having all the items sharing the same number, the same embeddings, and it only leverage the graph structure to make prediction without relying on the past knowledge about user and item. And this model is also studied through a number of ablation studies, which is like taking out certain part of it to study its performance. So the first study is only using the previous user dialog act, the most recent one. So is to measure like how many are needed for policy generation. The next one is without dialog acts at all. Yeah, and is to measure the importance of this past dialog acts in recommendation. And lastly is without the dynamic update of the user memory graph, and to see whether it is crucial for better reasoning. And so the result is presented in this table, and can be generally observed that this proposed model, or this proposed original model, performs better for both offline and online evaluation. For its ablation models, when only the previous user dialog act is considered, is still relatively competitive. When there is no history of past dialog acts, is still relatively competitive, which shows that the initial memory graph can be used, is sufficient for reasonable reasoning. But without the dynamic update of the memory graph, the performance is lower a lot. So dynamic update is shown to be crucial for the performance of user memory graph reasoner. Yeah. So when comparing this model with the memory network, it shows that the memory networks might not be as good for complex reasoning because of the triples are disconnected. So there's no possibility of joining all the path as compared to a lot. So dynamic update is shown to be crucial. Yeah, the dynamic update of the memory is crucial because when it's static, the performance is much worse for item matching rate.
Yeah, this is a function, of course, of the type of problem they're trying to solve, right? They're conditioning on having the past information from past dialogues make a impact on the current dialogue.
Yeah, the initial memory graph from the past. Sorry, I think the initial memory graph is quite reasonable for without the dialog X encoder. That shows that the initial memory graph is still reasonable, but then when it's not updated, then the performance without updates, then the performance lower a lot. Yeah. Yeah. So moving on for the memory network, is also not structure preserving, so they cannot align the entities for an output optimal policy. And static memory is often assumed, and static memory means that from the training, it's often assumed that the knowledge about user and item can be transferred to testing. But in this case, for zero-shot reasoning, it's not suitable because there's no knowledge from training carry over, and instead the graph is used for reasoning. And in comparison with the rule-based agent, the rule-based agent can be a good baseline, but then it always recommend the only dialog act it does is recommend, and it can be annoying for the user. And in comparison with the static pre-trained graph embeddings, overall the embeddings can provide a general representation of the original memory graph, but it lacks the ability to do personalized recommendation. And for discussion, the author looks at all the generated dialog X from the simulation of the MG-Convex dataset. It's observed that there were more recommendations made than expected. And this possibly because there's a patterns of non-recommendation X are frequently followed by a recommendation X from the users. And this makes the network tend to cater to these frequent patterns instead of perform more diverse kind of reasoning. And so the possible improvements is that the author hopes to focus more on more diverse and detailed reasoning. And he also says that human reasoning can be quite limited, given that in real world recommendation, there are a lot of candidate items. So future research will be focused on automatic reasoning, given that over a large scale of user knowledge. Yeah. And with that, I come to the end of my presentation on the experiments and results. Yeah.
Okay, let's thank Nham, Chengxin, and Victor for their presentation. Because we had quite a lot of discussion on this paper, I would like us to go ahead with the next paper. So while we're getting ready for the next paper's presenters, I've gone through some checking on this paper and I couldn't find the data set that they promised. So if anyone can find out where they hit it, then let us know. It could be that they ran into licensing issues or other things that prevent them from sharing it. And I would also encourage you to think about, okay, how you would originate a paper like this. Obviously, they came up with the problem and they had to collect the data set ahead of time, right? So they had to construct this data set, and it's no small feat because it's a fairly large data set. They had to construct a very elaborate user simulator and crowdsourcing agent. So those of you who are doing research that requires data set collection, you might want to strategize, from a metacognition level. Okay, why did they come up with this data set? How did they decide to do it? And why did they do it in such a way to support their research, right? How did they decide the scale of the data set? They could have collected something a bit smaller or much larger. And so all of these parameters that surround the collection of the data set to support the publishing of this paper and perhaps a few others from their lab, you want to try to examine from a metacognition network, level, so that when you apply this idea in your own research, when you have to gather data, you can think about, okay, well, I saw this example in this paper. I know why they chose the parameters that they did in order to encourage to be able to find this research. Many times it doesn't quite all gel together, right? You get some data set, it doesn't exactly show you what you want. So you should also think about on the other side of the fence, like if you were to collect your own data set, knowing what they actually presented, how would you have gone and changed the way they collect the data, right? So would there be a more optimal solution to that in terms of the rounds or the types of requirements that they had or restrictions that they put on the data collection, right? For example, they said in their user simulator, you must, as the user, you're trying to find this particular item, nothing else, just a set of one that you're looking for. Okay, so that's a simplifying, constraining assumption to be able to make the problem solvable. Okay, so Afrin wrote, there is a data set, but I don't know whether it's the same one. So if you guys can take a look into that, especially in this Scribe group, we can take a look at what Afrin was able to find from other places. Okay, I don't think it's the actual one, but multi-walls is a very large data set. It's used for many things, but it is yeah, another data set that other people in our group, like for example, Taha, who asked the question earlier, is also using. Okay. All right, let's go on to the next paper since it's now an hour past. So our next presenters can take over the screen share.
Hello, guys, can you hear me?
Yep.
Yeah, I'll share my screen.
Great.
You see the screen?
Yeah.
Okay.
You're good to go.
Okay. Hello everyone, my name is Hongfu and my group mates are Qiao and Zhou. We're going to cover this topic of towards knowledge-based recommender dialogue systems. And firstly, I will give a brief introduction and motivation of this paper, and then Qiao will give us more detail about the methodology proposed in this paper. And finally, Zhou will talk about the experiment and explain how the experiment exactly demonstrates the effectiveness of this proposed model. And first, okay. So as you guys, I guess you guys are pretty familiar with the recommender system and dialogue system. So I just give a quick skip. So the recommender system should provide some high quality of recommendation based on the user's preference, and the dialogue systems should respond to the utterance of the users with some informative natural language expression. So for the recommender dialogue system, it's just you just need to do both things. So for example, on the right side, there's a dialogue, there's a recommender trying to recommend the movie for the users. And so one thing I want to point out in this dialogue is the knowledge in the dialogue. So we can see the users want to get one he likes the nightmare on the L string. It's a kind of movie's name. So here it's just an item information. So for the some other information like the context information, which is not mentioned in this dialogue, but it could be like some directors' names or some actors' names or some actress names. Yeah, maybe it could be some useful information. So that's some knowledge in the dialogue system. Okay, so the motivation of this paper is trying to solve some problem. Basically, the conventional recommender systems just using some item information, just I mentioned that the movie name, like the Star Wars or some other items like this. So they don't actually model or give us some mathematic tools or something to deal with the contextual information in the dialogue. Like I just mentioned the director, actors or actress, because it's easy to follow that. If the users talk about some actors or actress he or she like, and there's a high possibility to recommend some movies of with the same actors or actress. So that's kind of thing like this. So in this paper, it tries to solve the problem to how to make better use of the contextual information and also the item information. So yeah, it's so the basic idea is pretty easy to follow. It proposed a knowledge-based recommender dialogue system. It's kind of an end-to-end framework to integrate both systems. It's easy to understand that for the recommender systems, it can provide some vocabulary bias with recommendation where it can try to improve the response to the utterance with high quality because it contains some maybe recommendational vocabulary in this response, and also you could maintain the multi-term dialogue. Also for the in return for the dialogue systems, it could indicate some users' preference in the dialogue, like I just mentioned in the example, like the item or the non-item, also the contextual information. That's yeah. For another things is that supposing that we don't have any preference information for the recommender systems, we can just use the dialog systems for some recommendation. It also tags the co-star problem. So the important things in this paper is that the knowledge graph incorporated. It's kind of external knowledge from an external link, which the graph is kind of bridge to the gap between two systems. Or yeah, that's the main idea of this paper, and it's easy to follow. So, and then my groupmate Ray will give us more details about the system and how the system is implemented and designed. Okay. So far, any questions? Sorry.
Oh, you have to stop sharing,
Okay.
so that I can share. Thanks. Can you guys see my screen?
Yes, we can.
Okay. Sorry, there is some technical issues. Yeah, never mind. I just go with this. So thanks, Hongfu, for talking about the introduction. I'll talk about how the method used in this paper. So we mentioned that the baseline recommender dialog system looks like this part. So we will have a dialog system, a recommender system, and they're connected based on the mentioned items in the dialog history. So the items are the things like movies or restaurants that this recommender system will recommend to the user. But then the motivation is, again, how can we bring these two systems together more closely? And so we consider here, by using the knowledge graph, the two systems can be more intertwined, because now we're considering the contextual information from the dialogue history, such as the things like informative entities mentioned by Hongfu just now. And after being processed by the recommender system, it will also provide a bias towards the word token generated by the dialogue system. And we'll take a closer look at how this methodology works. So first, let's understand what knowledge is being brought into the system. So they use the DBpedia, which is a large-scale multilingual knowledge base extracted from Wikipedia. So this DBpedia is stored in a form of knowledge graph, right? This knowledge graph consists of triples, including the entities, relations, and the entity too. So in this graph, the nodes are basically the entities, and the edges are the relations. Then the benefit of this knowledge graph is that it can directly connect the items and non-item information through this knowledge graph. So we take example of this Star Wars film, and this is the entry from the DBpedia. So we can see that very important properties, like the director of Star Wars is George Lucas, and is distributed by this company. So the user is very likely to see other films directed by George Lucas or this 20th Century Studios if they have seen Star Wars. So this is basically the intuition. And through this knowledge graph, we're able to infer this kind of information, and such that the recommender can make better use of the dialogue, both the item information and non-item information. So one distinction between this paper and the paper presented by the first paper is that we're only considering these kind of noun phrases, right? So I think in the first one, they also mentioned things like affordable, this type of properties, which are adjectives. But in this paper, we're not considering those cases because they will not be matched into as entities inside the knowledge graph. And so how can we bring the dialogue into the knowledge graph? So we perform this task of entity linking, which is also known as disambiguation of the entities. So in this task, the words of interest, like names of person, locations, are mapped from input text to the corresponding unique entities in the target knowledge base. So for example, in this case, Paris is the capital of France. So we can successfully extract these noun phrases as entities, and then we map them into the knowledge base. In this case, it's Wikipedia, but in our case, it will be the Wikipedia. So one thing to notice is that we're doing this disambiguation because one word, one entity could correspond to multiple entries inside the Wikipedia. So for example, the movie Avengers could also mean the comic books or the toys or Legos. So right, we have to decide which entry to choose from the context of the dialogue. And after this, we can connect both the items and non-item entities from the dialogue to knowledge base, right? So once again, we're trying to make use of the entities, which are noun phrases. And then we can construct a user profile as a set of linked entities. And so then we can see how can we make use of this knowledge graph, which they call knowledge enhanced representation. So we have an entire knowledge graph, which is very huge, consists of a lot of nodes and edges from the Wikipedia, and we want to adapt this into our task. So at layer 0, we initialize this embedding layer for all the nodes inside this knowledge graph. So this is the cardinality of the nodes of this knowledge graph. And then we apply the relational graph convolutional network, which was also mentioned in the first paper, to obtain a aggregated representation of the nodes by propagating information from its neighbors. Okay, so it should be straightforward as it's already been introduced. And then once we obtain this knowledge enhanced representation, we should connect this towards the recommender system. Okay, so remember we have obtained a user profile as a set of linked entities. Then we just basically do a lookup table operation that queries the knowledge enhanced representation from the knowledge graph representation. So we have this HU, which is a very basic form of user representation. And then we apply a self-attention layer to obtain the user representation T. So the self-attention is basically a weighted sum of all the vectors inside this matrix. So the weights is obtained using a softmax and some linear transformation. It's also commonly used in transformer. Then one thing to notice is that once we obtain this user representation, we can only recommend items, not the non-items. Like we cannot recommend directors towards the users. We can only recommend the movies. So we have to perform this masking that set non-item entities to the score to negative infinity, so that when doing the recommendation, we won't be recommend those non-item entities. Then after we obtain this probability distribution of a recommender, we can see how can we come back to the dialog system. So the dialog generation is very classic, which is also used by a lot of other papers. It's based on this transformer architecture from neural machine translation. It's an encoder-decoder framework for sequence-to-sequence learning. So the encoder basically encodes the dialog history of the user, then decode by generating a representation O at each decoding time step. So this, after we obtain this representation O, then we can have a probability distribution of the next token using this softmax. And one thing to notice that distinguish this paper from others is the use of this additional bias term. And this additional bias term came from the user profile of the recommender system. Right? So this F is a transformation of TU, where TU is the user profile we mentioned just now. So we can see closely that these two systems are become more intertwined than the baseline system. And so, as also mentioned previously, we predict the next token by combining the probability distribution of the words from both recommender system and the dialog system. And by using another weighted, a gated units, right? So this gate is PS, which is obtained from a sigma function based on this O, where O is the representation obtained from the dialog system. Okay, this is all for the methodology. Do we have any questions?
Do you guys have any questions? I think, again, it's we can go quickly through the introduction and the metrics for the evaluation, but it's definitely very helpful to study the model closely. Are there any questions? Is it clear how the recommendation systems and the dialogue systems integrated together to get prediction? And it seems, I mean, from the math, it looks pretty simple, but yeah, I wonder a little bit more about their experiments and their analysis about when the dialogue or when the recommendation system gives more weight to the prediction, but I guess we'll get to that soon.
All right, if there's no questions, then I guess I'll take it from here.
Okay,
so
yeah, go ahead.
Sure.
Yep, so now I'll move on to the experiments and results. So for the data sets used, so the main data set here for evaluation is the redial. So actually, this is a separate paper. So they describe the procedure on how they develop the data set is by using Amazon Mechanical Turk. So yeah, so they generated 10K conversations, yeah, and all the information is given here. And of course, aside from the redial data set, of course, they use the DBpedia. So that is the database for the knowledge graph. Yep. So the metrics used is separated into two. So it's the dialog portion as well as the recommendation portion. So for the dialog, they actually use 3 different metrics, 4 actually, but yeah, 3 categories. So these 2 are automated, and then the third one is a human evaluation. So let me describe the metrics a little bit. So first is perplexity. So actually, this is a metric that measures the fluency of the natural language. So a lower perplexity score is better. So that means the natural language is more fluent. So you can think of it as like an exponential of the entropy. So like the uncertainty. So that's another way of thinking like why is lower better. Right. And the second one would be the distinct 3 grams and 4 grams. So this is a measure of the diversity of the language that's generated. So this is like the ratio of the distinct 3 grams and 4 grams of the generated words. Yeah. So yeah, given here. And finally, is the consistency. So this is actually a human given score. So they had 10 human annotators called the consistency of the response, whether it makes sense in the given context from just 1 to 3. Yeah, so this is just human score. And so maybe I go through this table a little bit. So over here, it says redial as well. So here's a little bit of not confusion, but yeah, the terminology is not so great. So this redial model is actually from the same paper. So it's the CRS model that was used with this data set. Yep. So this was taken as the baseline. So it's a basic CRS, and the dialog system uses HRES, which is a separate system, and the recommender system uses autoencoder plus sentiment analysis. And the way that these 2 gets connected together is actually through the very simple this style where like they just have a switching network at the end. So there's no like intertwine in the middle. So they just use this this thing, yeah. So they just get like p-dialog separately, p-rec separately, and after that they just do this part. So there isn't like all these other parts which are intertwined. Okay, so that's the redial baseline. The transformer baseline it was developed by these authors. So it's actually just it's the same structure as the redial one, except they use the transformer for the instead of the HRES for the dialogue system. And as you can see, this paper's model, KBRD, actually performs the best for all of them. And I think they also like to highlight that the number of this portion, the diversity of natural language. So you can see that the original dialogue system here is not as good, far nowhere near as good as the transformer based one. Yeah. And so for the recommendation, the metric that they use is just recall. So they evaluate whether the top K items, so in this paper they use 3 different, so 1, 10, and 50, whether the top K items recommended by the recommender, it contains the ground truth human recommendation. So this is the label. And as you can see here as well, this KBRD performs better than the baseline in all categories. And just because this is being used in the next slide as well, so just to clarify, this KBRD means it incorporates dialogue only, whereas the K is the model that incorporates knowledge only. So so now let's actually move on to the discussion, which I think is probably more important. So over here you can see the first discussion is whether the dialogue helps recommendation. So yeah, so is there any benefit to doing both the dialogue and recommendation together like this? All right. So this graph shows the recall. So this is the recommendation metric. And then over here it shows the number of mentioned items. And yeah, so this is the comparison between all the models. So let's highlight a few things. So first, notice that more than 60% of the dialogues only contain 0 to 2 mentioned items. So it's similar to that of like cold start, where like at the start of the dialogue, there's very little mentioned items. So when I mention items in this case would be the recommended. So it's all the entities which can be recommended. So don't have stuff like the directors and stuff like that. So it's actually very important for the model to do well in this portion. And so what we can see is like, especially for the number, when the number of mentioned items is 0, so we see that the dialogue models perform better when there are no mentioned items as compared to the ones that just use the knowledge. So the dialogue models leverage on all these like non-item entities, right? So the things like the directors, the type, what they call it, like the type of movies, things like that, genre and things like that, to give recommendations. So that's why it actually performs better than the ones with the knowledge. Yeah, you can see the green one is lower than the red one. But then like when you see as the number of mentioned items goes up, right? So you see the contribution of the knowledge becomes more significant. So this means that like the graph, the knowledge graph, the RGCN is able to learn sort of like the intricacies between the items as well as the non-item entities, but all the entities. Yeah. And so what we can determine here is that like both of these information sources are helpful in improving recommendation. So obviously the knowledge graph helps in recommendation because that is literally the model. But what it also shows is that the dialogue side of it also does help the recommendations, especially for the early portions like over here. Yep. So the dialogue introduces contextual information, while the knowledge graph introduces structural connections, as well as all the other movie features. Yeah, so all the things that's between the movies. So the next discussion is the other way around, like whether the recommendation helps the dialogue. So this graph actually, not graph, sorry, this plot shows the words with high probability given a mentioned movie, and then based on the recommendation aware vocabulary bias. So these are all the words that with high probability. So over here, sorry, I put here. So the recommender system actually conveys important information back to the dialogue system in the form of the vocabulary bias. So this term here, right? So this leads to more consistent responses. So that's why the score is higher. Yep. And these words also serve as like explicit explanations to the recommendation results. So for example, you can easily see like these are the words which are linked to the Star Wars movie. And yeah, so this serves as model interpretability. So I mean, from these words, you can basically see that the recommendation does help the dialogue. And yeah, that's actually all for the discussion. So for the conclusion, so this paper introduced an end-to-end framework for CRS. It showed that the KBRD reaches better performance in both the recommendation side as well as the dialogue generation compared to the baseline. And it also showed how like the external knowledge can improve recommendation performance, as well as how the dialogue and recommendation systems mutually benefited one another. And yeah, so I guess that's the end for my section. So let's take in any questions.
Okay, let's thank all of our presenters first. So thank you, Joe, Chauri, and Hongfu for presenting. Do we have any quick questions about the work? So what are some comparison questions that you should be asking? Let's say you're a reviewer of this paper. What might you be concerned about? Okay, one concern that I have is, you know, they've done a comparison against the transformer, right? So that's their base system that they use to modify it. So they already get quite a big leg up from the transformer model. As you can see on Joel's screen right now, the transformer model brings the perplexity down quite a bit. So there's actually no improvement in perplexity, meaning the fluency of the output coming from the incorporation of recommendation. You know, it's basically dialogue is okay, not great, but it's improved over the previous switching model, because the switching model, whenever it switched to recommendations, it basically didn't have any input from dialogue, right? Whereas in this model, you are having a way to combine the predictions from both sides. Where it seems to be helping a little bit more is on the accuracy as well as the distinct n-grams, right, to the diversity of the output. And you can see that they sort of did the transformer experiment as a little bit of an afterthought, or they didn't have enough evaluators because they never evaluated the human aspect. You know, there's that one dash in the upper right table that's missing, right? So they did that maybe later, or they just distinctly didn't bother to evaluate that.
Oh, sorry to add, yeah. So the reasoning they give in the paper is that the output from the transformer is so different from the redial that they were worried that the annotators can tell the difference. I think that's the reasoning that they give, but not sure if it's a valid reasoning. Yeah.
Yeah, I find that a little bit suspicious myself. You know, I would lean towards giving that number and then saying, you know, put an asterisk and say, you know, we don't trust this number that came out of the system, but I wouldn't have redacted it out of any evaluation measure. So, you know, sometimes we do that for good reasons, sometimes not so good, but in any case, we don't have that number, so we can't say. Yeah. So the other aspects are, you know, to look at the other parts where Joel mentioned that the incorporation of the knowledge and the dialogue as separate components seem to help in the analysis. So when you do the discussion in NLP papers, we hope that you're looking forward to this type of analysis in your own work. So if you're going to do a conversational recommendation system, you should be basically asking these types of questions. You know, does one system help the other in some way, right? And try to answer that as best as you can. Of course, in your own projects for this course, you may be a bit more abbreviated than what they've done here, but it does definitely help to try to triangulate your results through different metrics. Okay, so that's very good. Any other questions or comments on this paper?
I think I also feel like, although the baseline results and their proposed results are looking similar in the table, in the plot in the next slide, I think it shows that their model is doing much better in the cold scenario, right? Because as the number of mentioned items goes, I mean, baseline and their model is showing like more closer results, but then in the beginning, the difference is quite higher, I feel like. So it might be showing that they can do it with less.
I mean, for this paper, I would have also liked to see a little bit more discussion about when in which turns the recommendation system has more effect, in which turns the dialogue system has more effect. As we've seen from a lot of other papers, it's usually a good strategy when you get some negative feedback from your user. You want to sit back a little bit and clarify exactly what is it you want. You don't go pepper them with lots of recommendations that are sort of irrelevant. So I think the dialogue manager is more important after you get negative feedback. But that doesn't seem to be discussed or validated here. It's probably some secondary analysis that they could do to do that. Okay. In the interest of time, let's go on to our third group. So thank you very much for our three presenters for the second paper. And we'll go on to our final paper of the afternoon.
Okay, let's share the screen. Can you see your screen?
Gangyi is starting. Yes, we can see your screen just fine. And
Okay.
going to be working with Zijin, yeah, for this paper. Great, go ahead.
Yeah. Zijin and I will share the paper of adapting user preference to online feedback in multi-round conversational recommendation. First, thanks for Zijin's active support and help me finish this lecture. And so let's start. In this paper, it proposed a novel user preference estimation model tailored by multiple rounds of CIS called Feedback Gate Preference Adaptation Network, or called it FPAN. First, it first presents users, items, and attributes as nodes in heterogeneous graphs, and then use graphical neural network to learn node embedding more to get models are designed in this model. So let's just start. This lecture is divided into 5 parts. In the introduction, I will introduce the content related to CIS, and in the background, I will mainly explain the scenario of multi-round CIS. Then next, I will explain the method, experiment, and conclusion of the model, respectively. Noted that the experiment part was presented by Zijin. After finish the lecture of this paper, I will share some insight about CIS. So we are familiar with recommender systems, and the previous introduction has covered a lot of basics of CIS, so I'll cover them briefly. The recommender system predicts a user's preference towards an item by analyzing their past behavior. Example, click history, visit log, rating on items, and others. So in this system, the most important point is implicit. The recommender system does not know what exactly the user like, and what it can do is to infer the implicit preference based on historical data. So recently, dialogue system attracts extensive research. We can borrow the advantage of dialogue system to build conversational recommendation. So with strong language capabilities, a conversational recommendation system can directly communicate with human users using natural language. Through this communication, it can get sufficient understanding of user preferences and make better recommendations. So there are 2 examples, but I'm going to skip this example because presenters have talked about it before. So CIS brings a lot of benefits. It elicits user preference by asking questions about attributes, which is efficient. And what's more, CIS only makes recommendations when the confidence is high, which improves user experience. So a good conversational recommendation system will adjust its estimation of user. Here I borrow the figure from the year. to illustrate multi-round conversational recommendation. Because this paper uses the same setup as the year. As the conversational recommendation is an emerging research topics, and the multi-round conversational recommendation scenario is the most realistic setting in research so far. In multi-round conversational recommendation, conversation session starts on the user side. User will initialize the attribute by specifying an attribute the user likes. Next, the CLS is free to ask his preference on an attribute or recommended items. Then the user needs to give feedback accordingly, either accepting or rejecting them. Then the CLS makes use of such feedback from the user. Based on the updated sets, the CLS takes the next action, asking or recommending. The repeats the above process. The conversation session ends until the CLS hits the user preferred items or reach the maximum number of turns. So the figure shows how the system helps the user find the desired items, small Italy restaurant in multi-round conversational recommendation. When the user initializes the preference of Italian, the agent asks a user whether he likes pizza, nightlife, and rock music in turn through the template-based utterances, and finally successfully hit the target item. In this setting, CRS is free to ask attributes or make recommendation multiple times. We use a round to emphasize one trail of recommendation. This is in contrast to the single round of conversation recommendation. The multi-round setting is more challenging than the single round one because CRS has more freedom to take actions. It can recommend multiple times, so it is more flexible. And let's see this paper's motivation. First, we can the rich online feedback at both attribute level and item level can be collected using multi-round conversational recommendation system. And the attribute level signals reflect the user's positive or negative preference to specific attributes, which are derived from user binary feedback to agent. And the item level signals reflect the user's negative preference to these recommended items, which is generally by the user's rejection of the recommended action. Although their previous work has investigated a variety of approaches in multi-round CRS setting, but they overlook the relation between attribute level feedback and item level feedback. Item level feedback is hard to utilize since the reason for rejection can be varied. That is to say, even if the agent recommends an item based on the user's current preferred attribute, the user can also reject it. So to better illustrate the motivation of this paper, there is an example in this paper. Giving negative item level feedback, the user rejects a red iPhone. The reason for rejection could be the attribute red color or the attribute Apple brand or both of them. Using feedback directly as a training instance reduces the affinity score for all attributes associated with the item. However, in this example, if the user indicates a preference for red, for example, the user said red is a great option. So the system can infer that the app brand might not be a preferred attribute because the user says she likes red, but he not like this red iPhone. So the Apple brand is not his preferred attribute. So it's clearly seen that there are a relationship between item level feedback signal and attribute level feedback signal. The relationship can be used to obtain higher accuracy of performance prediction. So it can be improve the performance of multi-round CRS. This figure illustrates the structure of the proposed feedback guided preference adaptation networks, or called it FPN. In this model, the user preferences are constantly adjusted based on online feedback. The FPIN consists of an offline presentation learning module that generates the initial embedding of all users, items, and attributes in the CIS. And in middle part, an online user preference adaptation module, which used to getting components to modify item level feedback and long-term performance respectively. Then aggregate the rich user feedback information to generate adapted user performance representation. Finally, in item and attribute prediction module, the user preferences on items and attributes are estimated by modeling the affinity between adaptive user preference representations with item embedding. So that's the model overview. Next, I will introduce the method of this module. So the first part, offline representation learning. In offline representation learning, first we construct a graph. Denote this is a tripartite graph. The set of nodes is denoted as user, item, and attribute, and the set of edges consists of two types of edge. The user item edge means the user interact with the item, and the item attribute edge means that the item contains the attribute. Then the model uses graph edge, which is a GCM approach to learn the representation of node on the graph, just so you know. And for each neighborhood depth, graph edge generates a neighborhood embedding with the aggregate function for each node and combines it with the existing embedding of the node. So in this formula, we can see the W is a weight matrix, and each embedding is we want to get. Finally, we can the final representation of the node is obtained by aggregate the representation of the different layers. That means different layer of each embedding. Oh yeah. Just as discussed earlier, using the negative item will directly affect all selected attributes, which inevitably affects recommended performance because rejected items have some of the same attributes as the target item. This is mean the rejected item might have some positive attributes. So we need to pay attention to them. Therefore, the relationship model between item level feedback and attribute level feedback is established by using the gating mechanism in deep learning, so as to obtain an adaptive representation of rejected items. Specifically, giving the user and positive attribute feedback provided in the conversation history, the embedding of these attributes are first aggregated into one vector, and this new vector represents positive signals at the attribute level. Then a gating module is to apply to adapt its initial embedding to the positive attribute feedback signals, achieving adapted item embedding. Then the getting vector is defined. We can see there is a symbol concat. Concat means concatenate all of the input vectors. Getting models controls the information propagated from the rejected items embedding according to positive attribute signals. Finally, the adapted atom embeddings are further aggregated into a vector to present the negative signal at atom level. Sorry, just under the left. This is adjusted atom embedding. Yeah, and this is the user adjusted embedding. They have the same operation. Utilize the feedback from attribute and items. And the user's negative feedback on the attribute can be utilized to balance the user's long-term and short-term preferences. So similarly, these are similarly as atom embedding, so we can get adjusted user embedding. Then by aggregating different types of feedback signals, user preference can be got. Adapting user embedding in the representation of final user's preference, not only the adapting user embedding and adapting atom embedding can be the get mechanisms, but also the attribute level feedback is involved. These two parts are marked in blue and gray, respectively. This representation can emphasize process attribute preference explicitly expressed by the user. The affinity score between the user and atom can be estimated as a dot product between atom embedding and aggregated user preference representation. Similarly, the affinity score between the user and the attribute can be estimated as the dot product between attribute embedding and aggregated user preference representation. So the trainable parameters for FPA are the initial embedding for node representation and parameters in graph stage, for example, weight matrix, and the parameters for the get mechanism, for example, weight matrix and bells. The setup here adopts the same optimization method as the year. Among them, the model uses the optimization group of BPR. That is, the score of the positive sample is expected to be higher than that of the negative sample as far as possible. And if you are interested, you can also refer to the year for specific positive and negative sample designs. To optimize the loss function of both item prediction and attribute prediction, it can also follow the practice in year and optimize the parameters by performing multi-task training. So next is deployment.
Yeah. Can you hear me? Hi, can you hear me?
Yeah.
Yeah.
Okay, so I will go over the experiment part of this paper. So we have two research questions that the paper would like to solve. The first is
Zijin, maybe we
yeah.
can take a couple minutes first. Sorry, I couldn't unmute. Do you guys have any questions about the model? So if you can go back a couple slides to where the workflow of the FPAN is shown. Yeah, so this is a great graph because it basically pulls in all of the information that's going on. And so I'd like you all to reflect a little bit about what's going on here before we continue forward, right? So, you know, we are getting aggregate on the right side of all of the embeddings that are coming from both the offline representation, which is the initial one, and then the adapted versions that are happening online. And so I'd like you to think about the choice of operators that they've done for each of these different considerations. So there's a lot of basic addition and averaging done in this work. Do you guys have any comments about this? So for example, in the top part on the blue, they have the user embedding, and they're gating it with the attributes that the user has said is negative. And then on the bottom part, they're gating the positive attributes and the negative items together to get information about what items should be modified. So let's go through this and see whether individuals in the audience can explain each of these different lines. You know, the blue, the orange, and the green, and the gray one, and reason about their construction. Again, our goal here is to think about why they chose this construction, and for you to think about, if you're executing a project similar to this, what construction would you use? Okay, so I'm hoping that some of you who are lurking today won't mind coming in and trying to help us understand what's going on. I mean, Gangyi already narrated a lot of the work and from the paper's description, but I'm hoping to get your own understanding in your own words.
Yeah, that's better.
Okay, so how about somebody else besides Zijin and Gangyi, especially from the support group? If you guys could tell us a little bit about each of these arrows and why they're just, why is it their representation in that particular way? And then why are they being added in this particular fashion? You know, we have two positive components and two negative components, and they're just simply, you know, added together to vector addition and subtraction. So why don't we start with the top line? Okay, the blue embedding, right? This E prime U. Okay, why is it constructed this way? Do you guys remember what they said? Taha?
Yeah, so I think they're saying that the rejection is usually sourced because of the negative attributes that is associated with an item, and that's why they're I guess they're trying to integrate this information to the user embedding, because it's in the end the features that creates this user. But then, so if I'm thinking, how would I do it differently? And I'm not quite sure why, like, not also do the same thing. I mean, for creating the user embeddings, why not also use the positive attributes as well? So if anyone can.
So you're saying maybe take a line like this through another gate.
Yeah, I mean, it seems natural to me, but I guess there's a reason why they not do it, and I'm not sure.
I think I can answer this question. Why we choose negative feedback here and put it in get matching them with user, because if user reject the negative attributes, then this means the user dislike this attribute. It reflects its current preferred, different from the past history preferred attribute. So I think this negative attributes is help to construct a short-term user preferred interest.
Okay, did everyone catch that? So you have a user embedding that's trained offline, but during the session, the user says, I don't like a particular item. And then you try to infer from that information which attributes that the user doesn't like. And then you try to reflect that in the updated information for this current session, whether the user's representation needs to be updated appropriately. So they've masked that out. You can see, I guess it's intentional here, that some of the blocks in blue are lighter color to indicate that type of subtractive behavior, which is what the gating mechanism is doing from the negative elements. So, you know, Taha asked about whether it would be making sense to use the positive attributes. You know, I prefer items that are red rather than I just prefer, you know, items that are expensive. And, you know, that is a possibility in creating the model as well. So it could be tried, but I guess we often agree that negative attributes force a much more broad change in the type of recommendation strategy in the items that are done. So maybe it might make sense to gate it or have a weighting coefficient in some way that might update that, right? So I can see the value of what Taha said. If you know you recommended an iPhone and it's like, oh, I really like Apple products, I'm already completely bought into the Apple ecosystem, then you know that would need to be reflected in some way in an updated representation of the user. Okay, let's pick one other one to reason about so that we're clear about that. I think going through the paper does help a lot, but it also helps us to spend a little bit of time conversing about what's going on. So maybe we can pick one of the bottom two, either the gray line or the green line. Anyone want to take a shot at narrating either one of these? Again, from the support staff or the general audience.
So I can give it another shot for the gray part.
All right.
So the lower part here are the items which are disliked, and then the green part is the attributes of the same items which actually are liked. So in a way, when we use this feedback in the lower part, we are, I think, just by doing this aggregation, we are just trying to make sure that although we are saying the system that we don't like these items, we have some favoring parts about these. So we are integrating that information in the embeddings of those items.
Yeah, I think this is exactly right. So I hope everyone gets that. Both of these are doing modifications of either the user or the dispreferred items in the opposite direction, right? So in the top part, we have some preferences of the user, but we have some negative items. So we want to subtract away that information from the user representation. So it purely represents a positive feedback, right? That part there. And on the bottom here, when we have a negative part, right, we are trying to, again, take the negative items and subtract away from them their positive influences, which we want to discount, and then add that in finally as a negative, right? It's a negative, I think. Yeah. So there is a negative sign somewhere on here that reflects that. Okay, so that's integrated all in the final embedding. So it'll be interesting when Zijin goes through the final experimental results to see how all of this does. Okay, thanks Taha for answering the questions.
One thing I'm curious about is, can we actually know that these embeddings are doing what they're supposed to do, or is it like a theoretical, like what we think they're supposed to do?
I think this is a really interesting question, and it's something that I hope all of you are thinking about. I mean, that exact question came in my mind when I'm looking at all of these embeddings. It's like, can we use probes or some other method of introspecting them, either by attention to actual items, like I throw a item at it and I said, okay, how similar is this item to a particular user embedding after modification or an item embedding after modification, okay? And similarly the other way around, right? Because you have all of these representations and you need to introspect whether they're doing their job correctly. So that intrinsic type of evaluation is very important if you want to proof check. I mean, again, I've warned so many people about this, and I think many of you have similar experiences. Deep neural networks just work, okay? But you have no idea whether they're working properly as designed by your model, or whether the math just happens to have the same shape and you get something out and it doesn't represent at all what you thought it represented. So to do good deep learning analysis requires that you think really deeply about intrinsic evaluation. Okay, it may be very hard to get, but definitely we have to strive towards that. So those are a great question.
Yeah, because like there's a lot of addition and subtraction going on, but how do we know that the weights aren't actually just adapting to these operations and just doing whatever they want?
Yeah, so I hope the paper answers that. I'm cautiously optimistic. So let's hear from Zijin.
Oh, okay, can we go to the experiment page? Thank you. So these are the two research questions we've tried to solve. And first is whether the proposed model can have a better performance on atoms and attributes than compared with the current CRS. And the second question is if we want to combine the FPAN with multi-round CRS, whether the performance will be improved. Next page. So for the first experiment, here are some details. And so for the data generation, we use the conversation simulation methods here to generate the data. And these are some training details that is used in the model. Next page. So here are the performance comparison in terms of AUC. So these two, the Con UCV and Year FM are the two baselines we use to compare the result, and the Yelp and Last FM are the two data sets. And here are the three the three models we tried, the paper tried. So from this graph, we can see that the one with the mark indicates the improvements over the baseline model is significant. And we can see that the FPAN, the approach in the paper can outperform all the baseline methods on both the two data sets and on both the two settings. And then we also compared with the FPAN without the graph structure and without the gating modules. So for the graph structure, it is used for the user attributes and item embeddings. And for the gating modules, it is used for adapting to online feedback. So we can see that all the three approaches outperforms the baselines. Next page. And then for the second research question, we want to evaluate the multi-round CRS with FPAN. And here is the setup. So basically, we just replace the RC part of the year model and replace this with FPAN. And here is like how they define the conversation state. Yeah. And so the entropy information of each attribute is used, and also they concat the attribute preference from the part and the conversational history, also the one-hot encoding of candidate atom. Next page. And here is the performance on the different multi-round CRS. So these four are the baselines. And our method is to replace the CC part with the F pan in the ear system. So we can see it outperforms the baseline also on both data sets and in terms of these two setups. So for the, and so we can conclude that the F-pan can improve the performance of the system by using it as the RC part component. Next page.
Yeah. Thanks for introducing the experiment part. Any question?
Oh, yeah, I do have a small comment here. Yeah, okay. On this page, yeah, so my comment is that I'm very happy to see the author of FPAN is able to achieve very high result compared to year on the last FM dataset, right? So, you know, year only achieved 0.429 on SR at 15, and FPAN is like 0.66. It's much higher. So I think what makes me particularly interested is that, you know, in the year framework, because the last FM dataset, the characteristic of it is that, you know, the attribute is more sparse, and the system has a hard time to ask good attributes. Then it has to continuously push recommendation to user and get updated. So I think it seems like the FPAN framework is particularly good at, updating according to users' rejection. And I'm very to see that, you know, the reflection stage in year didn't work quite well on this setting. And I'm very happy to see that, you know, the FPAN, they have overcome this limitation of the previous work. Yeah, I'm very happy to see that. Yeah.
I think it's also very much the case that in their dialogues, they allow the model to ask about multiple attributes in one turn. So, you know, they mentioned this at the end of section 5, right under figure 5's graph, that because their system is able to do that, it sharply reduces the candidate set very quickly. So that's why you see a very big marked performance gap. The other thing I'll just point out for all of you guys is when you see performance gaps like this, they're actually very, very significant because you shouldn't think of it in terms of you know, the success rate is improved 1%. You should think about it in the flip side, which is that the error rate has reduced by about 25%. Okay, so you know, when you get a very good performance, especially on natural language tasks like part of speech tagging or things that are generally accepted as solved, then you can look at the error reduction rate over you know, a baseline. So that makes sense to try to highlight at the 90% level. They didn't do a particularly good job of saying that in this paper, but it's quite significant. Yeah. Okay, yeah, go ahead.
So I'll continue to introduce the conclusion. The proposed model use GN to learn offline representation, consider the relationship between feedback signals, and use to get modules to aggregate online feedback information. And the experiment also shows that this model outperforms the state-of-the-art baselines in terms of user preference estimation. It also improves the conceptual component of CRS, and we can see that the CRS metrics can enhance the user experience. So
Go ahead.
it's a good paper because she considered to the relationship between atom level and attribute level and use a GNN method to learn the embedding. But we can also to think what we need to do next. Here is for a survey about the advances and challenges of CIS, which was released by Lab for Data Science lead by Professor He. And I would like to thank Chongming and Dr. Lei for their main contribution to the survey. Then I'm going to combine some of my insights and talk about some of the promising future directions for CIS. First, joint optimization of conversation strategy and recommendation engine. That is to say, the conversation strategy and the recommendation engine need good cooperation, but the existing work does not deal with this relationship very well. But how to deal with the cooperation between the conversation strategy and the recommendation engine information is very important. Second, make better use of conversational information and knowledge enrichment. One of the core of conversational recommendation is conversation information. So using NLP, we can then reach semantic information of user preferences and attribute semantic information of item, rather than the traditional recommendation, for example, the ID information. Using this rich semantic embedding and then using it in recommendation model will get better results. So one strategy to make CIS smarter is to incorporate more information. This information can be knowledge graph or multi-model information. Next, specific, more complex strategies and balance the long and short-term interest of the user. Because now the strategy considered by the existing work is relatively simple. We can consider more intelligent strategies, such as applying the latest research on reinforcement learning to the dialogue strategy of CIS, and how to better balance users' long-term and short-term interests, and intelligently recommend items of long-term or short-term interest according to the user's intentions is also an important issue. That's to me. When the user go on a conversation, we need to know the user's real interest, not only a balance between long-term and short-term, but also we need to info his interest now and give a better recommendation. In addition, there how to develop the database, as well as the development of better evaluation methods and stimulated user methods to better the CIS evaluation are some of the problems that need to be solved. Because CIS is a complex system, many other advanced domain technologies can be applied to CIS. Because of its complexity and real-world demands, CIS will become an important research field in the future. And in fact, it will become a part of our labs. So I think that's my thought. That's all. Thanks.
Okay, let's thank all of our speakers, Zijin and Gangyi. So Gangyi is coming from Prof. Zhang his lab. So he's one of the innovators in this area. And so I think this is a really good slide to end on because you, especially those of you in the second half of 6101, you've heard the first set of papers on conversational recommendation systems, and you know, you have to do a project. Well, look at this. Well, there are some directions that you could try for that. So I'll just want to reiterate the importance of thinking about your project. So if you go back to our document, which is over here at 6101-like choice, last week we had a short session to group all of our graduate students in first year thinking about their projects. So most of you are here. So you do need to think about what to do for your project. So again, we have the Slack channel, and in the Slack channel, especially on the projects group, you guys have already started to talk with each other, but also more on the SOC PhD year one. So please do spend a little bit of time talking with me right after this session. Okay, I'll end very soon. So those of you who want to stay on, we'll spend a couple minutes, maybe about 15 or so, to talk about it before the next meeting that I have with other students. Okay, so with that, that's all for today. We'll have next week, we'll have our normal first day project consultation slot. So I hope by then all of our 6101 students for the second semester will have grouped into maybe 2 or 3 teams. Okay, thank you very much for everyone who was part of today's session, and a big round of applause. Remember that we need all of the people who are in the Scribe section of week 9 to contribute to fixing up everything in the Scribe notes, which were again advertised on the general channel a bit earlier on. So you can go through that link over here and then help to clean that up before the end of next week. Okay.